To continue our discussion on the quantum theory, let us look at a few things such as hydrogen spectra. We will see this series, the Palmer series, Lyman series and so on. We will talk about the correspondence principle due to Bohr, and then we will do a few go over a few experiments which have established the quantum nature of matter that we see. So, we talk about Stern-Gerlach experiment, we talk about the wave particle duality, and right now we just talk about the particle aspects of light, and they would be shown in two experiments called as the Compton effect and the photoelectric effect. Okay. So, what happens is that you see a experimental setup where it is only a schematic setup. So, there is a gas discharge tube that contains hydrogen. So, why we study hydrogen emission spectrum to begin with is that hydrogen is the simplest atom which has got one electron and one proton, and so it is just a one electron atom and the simplest one, and also that hydrogen is there everywhere. So, we start with this hydrogen spectrum and try to understand that what are the features of that. And so, here there is a gas discharge tube containing hydrogen. So, this hydrogen comes out and it passes through two slits as it is shown here, and then either a prism or a grating here prism is shown, and they are made to fall on a spectrograph or this strip that you see, the black strip, and the black strip is shown here where you see different wavelengths such as there are these this has to be in 0.46. All right. So, now you see that there are various wavelengths that are shown on the screen. So, what happens is that this hydrogen atoms being discharged from this tube, so they absorb energy and go on to these higher energy levels, and from the higher energy levels, because these have very short lifetimes, they cannot stay forever there. So, they quickly come back to the lower levels or the ground state, or ground state is just a sort of a quantum energy state, that is the lowest energy state, and then they sort of emit frequencies or emit photons which have these frequencies which you see there. So, these is the emission spectrum of hydrogen atom, and you see a red spectra at 6562 angstrom or 656.2 nanometer, and there is a blue green, there is a blue violet and so on. So, these spectra are seen due to the emission lines of the hydrogen atom. Now, these electrons, they absorb different energies, so they go on to different excited states, and it is also true that they do not have a one step decay onto the ground state. So, they take different routes for coming back to the lower energy state. So, when I say a ground state, you should interpret it as lower energy states, and this is what happens, and that is why you see that on the plate or on this photographic plate that you see there are these lines that are produced. There is something very interesting that happens here. You see discrete lines from red, blue, green and so on, and then you see here it is almost continuous. It is shown as black, but there is continuous shades of lines that appear here, and this is called as a series limit, and it is Balmer who found an empirical formula for these wavelength of these emitted lines that you see there. This 3646 is something that we just saw there, and in angstrom. So, this is written in nanometers. So, this is it is about 364 nanometer or 365 angstrom rather, not nanometer. So, this 3646, and then there is a n square divided by n square minus 4, and this is in angstrom. So, that is the wavelength of these lines that he could fit. So, this n equal to 3 is called H alpha line, n equal to 4 is called H beta, n equal to 5 is called H gamma and so on. So, these are the lines which are called as the H alpha, H beta, H gamma and so on. Okay. So, these are the lines, red lines and blue green lines and so on. So, that is what it is that Balmer found out, and he was able to predict 9 lines of this series. Rydberg came and this was I'm sorry, this should be 1890. Okay, so there's a correction here, please note that. So this 1890 Rydberg expressed this Balmer formula. He found it more convenient to write it in terms of the inverse of the wavelength, and remember, the inverse of the wavelength appears here because the energy is actually proportional to the inverse of the wavelength. So that's why if you take h cross equal to 1, c equal to 1, so energy is nothing but 1 over lambda, and he expressed this 1 over lambda as RH into 1 by 2 square minus 1 by n square, where n equal to 1 will give the Balmer series and then the Lyman series and so on and so forth. So n equal to 1 is the Lyman series and Balmer series, Paschen series, bracket and Pfund series. And where do they lie? They lie in the ultraviolet region of the spectrum. Balmer series is more in the visible or ultraviolet. These are in the infrared. And just to remind you that we have these visible range for 4000 angstrom to 8000 angstrom, and so this corresponds to the violet end and this corresponds to the red end, and we remember it by this this kind of VIBGYOR, that's violet, indigo, blue, green, yellow, orange, red. And so it's the same formula as Balmer, the same empirical formula, but expressed in terms of the inverse of the wavelength, with RH as the Rydberg constant, which is given by this value 10967757.6 meter inverse. And as I said that, if you put this 1 square minus n square, where n equal to 2, 3, 4, 5, then it corresponds to the Lyman series. Now you see that it's 1 by 2 square minus 1 by n square. Of course, there's a bracket everywhere that is missed here. So 2 square minus n square, this is called the Balmer series, which is what Balmer wrote down. And there's a Paschen series, which is 1 by 3 square minus 1 by n square. Then there's a bracket series 1 by 4 square minus n square, where n equal to all these 5, 6, 7, 8. So you see that when you have n equal to 1 in the first term, you have all n's 2, 3, 4, 5 all the way up to any number that you can think of. So as I said that electrons absorbing the energy because of this discharge, electrical discharge, or maybe putting them into high temperature, exposing them to high temperature, they absorb that energy and they go on to different levels, and these are the different levels that we are talking about. So emission from n equal to 2 to n equal to 1, or n equal to 3 to n equal to 1, n equal to 4 to n equal to 1 is called as a Lyman series. Similarly, these n equal to 3 to n equal to 2, 4 to 2 and so on, they are called Balmer series. They lie in this region of the spectrum, which is shown here. It's visible to ultraviolet, which means that it is around this region basically, and then you have an infrared region, which are here, which are all the other series wavelength. Okay. So these are the hydrogen lines, the emission lines of the hydrogen spectrum, and when we say lines, we mean a wavelength. Okay. So for heavier atoms, such as say alkali atoms, which are lithium, sodium, potassium, etc., the Rydberg formula is actually modified as this, which is 1 by lambda equal to r. R is again a Rydberg constant. Let's just come to that. So it's m minus a minus 1 by n minus b whole square, m minus a whole square minus 1 by n minus b whole square. R is the Rydberg constant for a particular element. RH was for hydrogen atom, and A and B are really constants for a particular series, that is all the series that you saw for the hydrogen atom. M is an integer fixed for a given series, and n is a variable for that series. So there are transitions from n to be a variable number to m, and m is lesser than n. So, this is how the this Balmer series, or rather the Balmer formula was or the Rydberg formula was modified for these elements, the alkali atom alkali elements. Okay. So, you see here there is a diagram of lot of transitions that are shown there. So, these Lyman series and Balmer series, which are just pictorially shown there. So, now from any of these lines there is a transition to these n equal to 1 state, which is called as say the ground state, n equal to 2 is the first excited state, and you know that this the formula is minus 13.6 divided by n square for the energy of the hydrogen atom. The electron has this energy in different levels, n equal to 1, n equal to 2. So, that is why these energy differences, as you go higher up in n, they decrease, and this is just schematically shown. So, these are Balmer series, is also called as Ritz and Paschen series, and Brackett series and Pfund series, and so on and so forth. Okay. Now, this ionization of hydrogen atom is taken as this thing, which is nothing but minus 13.6 electron volts. So, if you give that energy when the hydrogen atom is in the lowest state, n equal to 1 state, it will lose that electron and will become an ion by losing that electron, or it sort of becomes kind of positively charged without that electron. So, that is what it is. But however, there is one problem with this diagram. Not all these transitions that are shown by these vertical arrows that you see, either black in color or green, blue, red in color, they are not always seen. And so, there is something more that is required in order to define these emission spectra or even absorption spectra. Okay. We do not discuss absorption spectra, which is pretty much more or less like the emission spectra with some minor differences, which we do not want to elaborate here. So, some of these lines are not seen in spectrographs, and there exist certain selection rules. So, this is very important thing. There are certain selection rules that dictate which lines will be present and which lines will be absent. So, I just write it here. It is E n equal to minus 13.6 divided by n square in electron volt. So, because of this selection rule, that it demands that some extra condition is needed. And what are those extra conditions? These Bohr stated that there is some correspondence principle, and it basically it does not give you the selection rules per se, but it tells you that what are the if there is a selection rule that's exists in some region of the quantum numbers n1 and n2, these selection rules would also exist in another very large a limit of the quantum numbers, another n1 and n2, which are very large ones or very large numbers. Okay. So, the correspondence principle is really stated as the following in these two 1 and 2 statements. So, it says that the predictions of the quantum theory on the behavior of any microscopic system must correspond to the principles of classical physics, and that is in the limit of large quantum numbers. Okay. And so, basically we will just elaborate on that in a moment. And so, the selection rule should be valid for all quantum numbers, and thus a rule valid for small n, which let us call it as a quantum limit, should also be valid for large n, which we will call as the classical limit. Okay. So, that is an important thing. So, if you really think that there is an absorption of radiation, and this radiation gives you sort of there is a transition from a particle from one quantum state to another quantum state. So, this is actually the EF minus EI, which happens because of this quantum because the energy absorbing a radiation of quantum h nu. So, the frequency of the emitted photon if a particle goes from a lower energy state to a higher energy state, or it sort of decays into from a higher energy state to a lower energy state. And this is exactly what we said, that the hydrogen atom that absorbs this energy and goes on to a higher state, and then because of the low lifetime in those higher energy states, they decay. So, this is equal to sort of EF minus EI equal to h nu. So, EF minus EI by h equal to nu. So, this goes from so its EF is equal to, say for example, NF h nu, EI is equal to NI h nu, where I and F are the initial and the final state. So, EF minus EI, this is equal to NF minus NI h nu. And so, it is very clear that if there is one photon that is emitted in going from a higher level to a lower level, or a photon is absorbed in going from making a transition from a lower level to the upper level, this has to be equal to 1. Okay. So, NF minus NI has to be 1, because that is the energy of one photon, that is the so with frequency h nu. Okay. So, this is the selection rule that which says that NF minus NI is equal to 1. That is a selection rule, and this selection rule will hold no matter what the values of n's are. So, if you are really here at very large n, which is shown as n equal to infinity, or if you are at very small n, it does not matter, but these things will this selection rule will hold, that NF minus NI equal to 1 in this particular case that we are talking about. Okay. Let me give you another example. So, if you think about again we are talking about the hydrogen atom. Okay. All right. So, we are talking about the frequency of an electron in a Bohr orbit you see this sort of the expressions for velocity and the radius that we have found out earlier. So, this is equal to, let us call it as nu 0. So, let us call this as this nu 0 frequency. This is equal to V over 2 pi r, and this is equal to 1 by 4 pi epsilon 0 square m e 4. This was done in the last day, so I will not repeat it here. It is and 2 over n cube. So, that is the frequency in a given Bohr orbit, and you can find that out by, because you know V and you know r, the radius of the orbit, and this goes as 2 over n cube with this factor that is written here. Okay. Now, the same nu, if you are talking about two levels, any two arbitrary levels which could be large, it is again 1 by 4 pi epsilon 0 whole square, and there is a m e 4 by 2 pi not 2 pi, there is a 4 pi h cube, and then we have a 1 by nf square minus 1 over ni square, and let us take nf to be equal to some n2 and n1 to be say some n, and so nf to be say n minus 1 and ni to be equal to n, and if you put it there, this you remember that this factor is same as that factor, the factor that you see here is same as that. So, if you look at this bracket that we have written here, so this is 1 by n square, and this is like this is n, so we have a n square and a n minus 1 whole square. So, there is a n square minus n minus 1 whole square. So, we can open up the bracket, which is n square, and there is a 2n, and then there is a 1 there. So, this n square would cancel, and we have this equal to 2n minus 1 divided by n square n minus 1 whole square. Okay. So, in the limit of large n, so this goes as so 1 can be neglected in terms in front of n when n is large, or 2n when n is large, and again 1 can be neglected in front of n. So, in the denominator we have n to the power 4 and we have 2n in the numerator. So, this goes as 2n by n to the power 4, which is nothing but 2 divided by n cube, and that is the factor that you get it here as well. So, it really does not matter that whether you are at large values of n or at small values of n, the frequency in the limiting case when n is very large would still be given by this formula that you see here. Let us call it as equation 1. So, let us go into an important discovery which has happened at in the the early 1900s and so on, and that is called as a Planck's radiation hypothesis. Okay. And it is often called as a Planck's law as it is written here. I would still like to call it a hypothesis because this is the experimental data for the radiated intensity or the radiation intensity due to a black body. So, black body is you can read up the definition. The black body is basically there is a whatever is incident is absorbed. Okay. So, there is or rather it has this emissivity equal to 1. So, that is why it is called as black. It is completely sort of absorbs all the radiation that is incident on it. So, like sun is a black body. Okay. So, here we are showing this, if you see the right picture, that will be even better, which shows the radiation intensity as a function of wavelength. And you see that there is sort of a non-monotonic behavior for all the temperature. Of course, this is at 5000 Kelvin, which is large temperature, then it is 5500 Kelvin, 5000 Kelvin, 4500 and so on. So, what happens is that there is a peak behavior that is seen, but the peaks shift slightly towards larger wavelength. That is one thing. And so, what it means is that if you start hitting up an object, the emitted radiation changes its color. Okay. So, changes its wavelength, and the emitted radiation has first it becomes white hot and then red hot and then blue hot and so on. So, these emitted intensity is what is plotted as a function of the wavelength. And one feature, as I said, is that there is a non-monotonic behavior, and this non-monotonic behavior could not be explained by what is called as a Rayleigh-Jeans law, okay, which only shows that there is a the classical theory says that, which goes as 8 pi nu square by c cube kt. So, this tells you that it should go infinitely large at low frequency or low frequencies, and there is these this side is by this Wien's law, which talks about large frequency. Remember that in the left figure we are talking about frequency and in the x axis, and in the right figure we are talking about wavelength on the right figure, and this is intentional. It is just to remind you that the frequency is inverse of the wavelength and so on. Okay. So, E is equal to h nu, or it's equal to Hc over lambda. Okay, so that is an important thing that you should remember. So if you look at the left figure as a function of wavelength and the right figure as a function of frequency, they would sort of interchange their high and low notions. Okay. So, what was very important at that time is that both these Rayleigh-Jeans and Wien's law, they could not explain the observed spectrum or the non-monotonicity that is observed in this spectrum. And that led Planck to propose that the energy density of radiation, which between frequency nu and nu plus d nu, you can equivalently write it in terms of the wavelength by using this relation that we have written here. So, u nu d nu is equal to 8 pi h nu cube divided by c cube, and then there is a exponential h nu by k t minus 1, and this helps you to obtain this non-monotonicity in this observed intensity spectrum. And how one calculates is the following, that one can calculate the average frequency or the average energy, say for example, by using this frequency. So, this is like this and h nu, and then you can calculate a nu u nu d nu from 0 to infinity, and then you multiply it by c. That will give you the intensity. The c is the speed of light, or this the speed of this radiation. Okay. And there could be some factors which could be there, but in any case this is what has been proposed by Planck, and that is why I call it as a hypothesis, because this had no sort of proof that has been presented by Planck at that time. And it was later Bose, he came and proposed this form for bosons. So, photons are known as or they are called as bosons with certain symmetry properties and statistics, and he consciously sort of derived this spectrum, or rather this distribution function, which reproduces the black body radiation. Okay. But one very important thing that emerges out is that what Planck said, if you keep these radiation, electromagnetic radiation, or whose quanta are known as photons, then you can never keep the number of photons to be fixed. The walls of the container is always going to emit and absorb radiation, rather it will exchange radiation with the surrounding, and the packet in which it exchanges radiation, it is a quantum, and that quantum, the energy quantum, has a value which is h nu. So, this was quite important in those days, and the birth of all these quantum mechanical ideas of quantized energy levels that follows afterwards. Okay, so let us go into another quantization, which at that point this Stern and Gerlach experiment. Stern first did it alone in 1921, and in the same year later on he repeated the experiment with Gerlach in 1921. So, there is an oven that you see, which is of course at high temperature, or which produces high temperature, and there are Ag atoms, silver atoms. And if you ask why it is Ag, why not anything else? So, first of all, Ag is a stable atom. Ag is a little kind of big atom, and these atoms have the electronic configuration. It has 47 electrons, and if you start filling up, you will see that 46 electrons form a filled shell, and plus that one electron which is in the 5s configuration, that is only free. So, it is like a one electron atom. So, you get the properties of an electron manifested by choosing Ag. Of course, there are other ones which have one electron in the outermost orbit, but they are small atoms, and they would be vaporized inside the oven, and nothing will come out. So, that way silver was a better option, or rather at that point was the only option that was available. Okay. So, it was sent through two collimator slits, and then it was sent through two pole pieces of the magnet, you see that S is the south pole and N is the north pole. But there is something interesting about these pole pieces. There is a sort of this roof of this is like this roof of a house, and that makes this magnetic field to have gradient in the z direction, and that was very needed, and it's shown in the right panel. You see that there is a north pole and the south pole, there is a bending of the field lines, and the magnetic field is not uniform here. Okay, so this is an important thing, and understood that this why do you need this B to be non-uniform? We just come to that in just a while, and let me sort of then do this simple calculation which tells you that this field is indeed needed to be non-uniform. So these electrons have magnetic moment. So we can write electrons to be E minus, have magnetic moment, and this magnetic moment would interact with the magnetic field. So, let us see what happens because of that. So, there is a force that arises because of this interaction, and that force is given by, for simplicity you can think this to be the z direction, which means that B has only a variation in the z direction. So, B has z direction dependence. Okay. So, f of z, that is f in the z direction, is del del z of mu dot B, that is the interaction term, and that is how the magnetic moment of the electron, the only electron that we are talking about, the rest are all filled shell of silver atom. So, there is a mu dot B interaction, and so the force is obtained from an interaction potential by the gradient of this. We are just talking about the magnitude. There is indeed a negative sign, it is a negative gradient, but so this is equal to mu z del B z del z. Now, this is where the non-uniform field comes into the picture, because if field is uniform, then we do not have sort of force that exists, okay, because mu is constant and B has a variation in the z direction. So, now if you really think of mu z to have any value, so classically mu z has values between plus and minus mu. Okay. So, which means that if that is true, then what you should get here is that there is a patch. I will draw it with a color. So, you should get a patch here of silver atoms, that is on this detector or the screen. You should get a patch of that, but what was seen experimentally is that there was no patch, and there are two sharp images. Let me again use another color, and there are two patches, there are two just sharp spots that are observed, and so this is observed experimentally and not the patch. So, this is not observed. So, that tells you that it takes two extreme values, but do not take any value that is in between that, in between these two values. And this tells you that this mu actually has only two possible values, and in those days it was referred to as the space quantization. But now we know that this is called as basically the quantization of the spin, the electronic spin, and this mu is proportional to the spin with some constants and so on, and this is, so mu z is corresponding to this it corresponds to the z component of the spin, which has two values which are known as h cross by 2 and minus h cross by 2. And this is interesting because h cross has the unit of angular momentum, and this is, the s is known as the spin angular momentum. Okay. And so h cross has a value which is 1.0546 into 10 to the power minus 34 joule second, and this is called as a Planck's constant. This we are quite familiar with this. So once again, this quantization of the z component of the spin, and the fact that this mu, which is not a classical object or quantity, rather it is not a classical quantity as it was thought about, that there is this electrons have a magnetic moment, and this magnetic moment is just a classical variable which can take values, any value. So these quantization of spin or spin angular momentum is a main inference of Stern-Gerlach experiment. Let me in short write SG experiment. Now, apart from that, there is a very important inference that emerges out of this experiment, which was less stressed about, and one should talk about that as well. Before that, you have to understand that if the magnetic field varies in the x direction, then we will have a force in the x direction, and then we will have this again two spots, but that would correspond to Sx equal to plus h cross by 2 and Sx equal to minus h cross by 2, where Sx is the component of this angular momentum, spin angular momentum vector, or if the magnetic field is non-uniform in the y direction, then we will have Sy and so on, okay, having values which are plus h cross by 2 and minus h cross by 2. Okay. So, let me sort of give you another perspective of this Stern-Gerlach experiment in addition to the spin quantization. We will talk about a series of experiments. So, SG experiments, and let us just put them as thought experiments. So, there is a oven that is there, which is what we have shown. So, there is oven, and there is a collimator. Let us not draw that, but there is a collimator, and there is a we will call it as SG Z cap, okay, which means that the magnetic field is non-uniform in the z direction. So, that is SG is for Stern-Gerlach, and Z cap is when the magnetic moment is or the magnetic field is non-uniform in the z direction. Okay. And then of course, you will have these Sz plus and Sz minus coming out, and then it can send it through this again this SGZ. So, this is that Sz plus component. So, Sz plus this is just a new notation used for these plus h cross by 2, and Sz minus that corresponds to minus h cross by 2, the notation. Okay. And what we do is that suppose we clip this thing. So, we put a stopper for this Sz minus. So, this is blocked, and so we will again send it through another SGZ apparatus, and then we have this Sz plus, and there will be no Sz plus component. I mean that makes sense. So, output is only that of say you call this as notationally you call it as an upspin and this you call it as a downspin. So, there is only an upspin that emerges. So, this is the output in two such SG apparatus. Okay. Consider a second case where we have there is an oven here and forgotten. So, so there is this now we have a SGZ and again we let this SG plus go through and send it through say SGX, okay, which means the magnetic field is non-uniform in the x direction or along the x direction. So, again we block SZ minus component. So, it is blocked. Okay, so, what will come out is SX plus component and you get a SX minus component. Okay. So, we will have corresponding to SX we will have a component which is having an eigenvalue plus h cross by 2 and minus h cross by 2. We do not want to represent it by up and down because up and down are the the eigenstates of SZ. So, so you get Sx plus and Sx minus. So, these components come out. So, that is the output for this case. Okay. Now, this is it makes one think that whether this output actually has 50% Sx plus and 50% Sz plus and 50% of it is Sz plus and the other 50% is Sx minus and Sz plus. Okay. So, is that the composition, but if that is a composition then that runs into a trouble as we will see in the third step. So, we add one more layer of complexity and put this oven and put a SGZ, that is the first and again let only the SZ plus component go through, the SZ minus 1 is clipped, this is made to go through a SGX and then of course SX plus is let go while Sx minus is blocked. So, here we have blocked Sz minus and here we have blocked Sx minus. So, these are blocked. And then this is made to pass through finally another Sz. Okay, that means the magnetic field is in the non-uniform in the z direction. So, you have this as Sz plus and Sz minus. So, that is the output that you see here. Okay. Now, this is strange because in the first case itself you have blocked this Sz minus. Okay. So, if in the second stage you would have thought that you have these n0 by 2 number of atoms. So, n0 is the number of atoms that are emitted from the oven. So, if there are n0 by 2 and n0 by 2 in the second stage which comprise of Sz plus Sx plus and Sz plus Sx minus, and then you have blocked the Sx minus, and then you have to interpret that the final these output in presence of these three sequential SG apparatus is Sz plus Sx plus and Sz minus Sx plus. Then that is not true because what's observed is that you get Sz plus and Sz minus. So, that tells you that even though Sz minus was blocked in the first level itself after the first SG apparatus, it still manifests in the final outcome. and so it changes the state that you see here at the final outcome, and that tells you that these Sz and Sx are really incompatible observables. So, this is a very important statement. Sz and Sx are incompatible observables. They cannot be measured simultaneously. Okay, so, this is a very important statement that two components of spin cannot be measured simultaneously, and this would be reflected later that if there are two observables and these two observables they correspond to two different operators, these two operators, if they are incompatible or they cannot be measured simultaneously, then we said that this Sz, Sx, the commutation of them is not equal to 0, and indeed the Sz, Sx commutation is not equal to 0, and it is in fact the third component which is Sy here. So, the general statement is that if there are two observables and they correspond to two operators and these two operators do not commute, then they cannot be simultaneously measured, or if they cannot be simultaneously measured, then they do not commute. Okay. And these two are non-commuting operators, and we will see that x, that is the position variable and the momentum variable, or these operators or their corresponding operators are non-commuting observables or non-commuting entities. Okay, let us go through this Compton effect, and why do we do Compton effect? We want to sort of understand the particle nature of this radiation. Okay, and in some other experiments we will see that they show up as the wave nature of the electromagnetic radiation shows up, but here we will talk about the particle nature and sort of how do we show that particle nature. We will show that that they obey these energy momentum conservation relations and so on, which are applicable to particles. Okay. So, what do we have? We have an X-ray source here where photons are coming out, photons of wavelength lambda, they are coming out and they are passing through collimating slits, and they are on a target. In this case it is taken as a graphite target, and these photons finally go and get collected in the detector, and because photons they are shown by this wavy line. So, there is an incoming photon has a wavelength lambda and the outgoing photon has a wavelength lambda prime, and the angle by which it is scattered is called as a scattering angle, and the detector is kept at that angle. So, you can understand the detector can be placed anywhere on these dotted or the dashed lines and placed in an angular fashion. Okay. So, this is the experiment that Compton did in 1923. Okay. And if you really want to see the the actual experiment, so there is a X-ray source, and then the photons come out and they hit a target, and they then hit this crystal spectrometer, or there is a crystal there, and then finally get detected in the ionization chamber. So, this is the detector that we have drawn on the periphery of a circular arc, and but there is this crystal that we haven't shown, but this in the actual experiment this crystal was used. It of course won't matter to us because we will write down energy momentum relation between the photon which is coming from the X-ray source with some electrons that is there. So, there is it's just like a classical scattering. So, there is an electron there. So, the photon collides with the stationary electron and then gets scattered, and we measure the scattering angle. Okay. So, let us draw this thing. and you can sort of simply draw this, that, or rather schematically it can be shown. There is an incoming photon coming with a frequency or the momentum k I. Of course, photons have they carry momentum, and they have a pressure associated with that, which is called the radiation pressure, or this radiation intensity, which black body radiation measures. And then there is a scattered photon, which is shown by the wavy lines. That is the scattering angles theta. It's also true that the electron also gets scattered, which is called as a recoiling electron in a different direction. Let's call that angle as psi. Okay. So let's see in Compton effect what actually happens, particularly in experiments. So if you allow the monochromatic beam of X-rays to fall on a crystal, specifically a graphite crystal, if you know, graphite is a 3D form of graphene. So these X-rays will be scattered from the target, from the atomic nuclei, as well as from the orbiting electrons of graphite. So the scattering from the nucleus is elastic, so that there is no change in energy, while that from the electrons is inelastic. So this causes a shift in the scattered wavelength, and we shall precisely calculate the change in wavelength because of this scattering. We can calculate a delta lambda as a function of theta, which means that this is the incoming wavelength, and this is the scattered wavelength. So lambda minus lambda prime, or the other way around, maybe lambda prime minus lambda is equal to delta lambda, and this delta lambda can be found as a function of theta. And how we do that is, let me draw a simplified picture for our purpose. So this is the photon, and there is a stationary electron that is there, and then there is this photon that so this is the incoming photon, and so this is the recoil electron, and this angle is theta, and this angle, let's call it, instead of psi, we call it phi. So this is electron and stationary electron. So there is a photon coming, and the photon has wavelength lambda, momentum p0, and energy e0, and so this is the electron. So this is scattered photon with lambda prime, and this is recoil electron. This is say k and p. Okay. Initially it's at rest. So this is, say for example, energy E1 and P1. Okay. So what's the momentum conservation? The momentum conservation says that it's along the direction and perpendicular to the direction of propagation. So this momentum conservation yields P0, which is the initial photon momentum. There is no electron momentum because it was at rest. So this is P1 cosine theta. Theta is this angle, so it's in the direction of propagation, and P cos phi. P is the recoil electron momentum, okay, and K is the kinetic energy. All right, so this is let's call it as 1A, and perpendicular to the direction of propagation, which is P1 sin theta. This is equal to P sin phi. Okay, so this is in the direction of propagation, because perpendicular to the direction of propagation, there was no initial momentum either of the photon or of the electron, but for the photon and the electron, they are in opposite direction. One is in the positive y axis, if you like, because this is, say, x axis and this is y axis. So positive y axis and negative y axis, they would simply be equal, because there was nothing in the initial part. Okay. So if you square 1A and 1B, Then we get P0 minus P1 cosine theta square is equal to P square cos square phi. So, this is 2a and this squaring 1a and squaring 1b, we get a P1 square sine square theta equal to P square sine square phi 2b. I hope all the variables are clear and all the angles etc. These all these things that are written, they correspond to, some of them correspond to those of photons and some of them correspond to those of electrons. So, if we have these written as 2a and 2b, what we do is that we add 2a and 2b. And that gives us P0 square plus P1 square minus 2 P0 P1 cosine theta is equal to P square. Let us call that as equation 3. So, that is adding 2a and 2b. Just to remind you that we are trying to arrive at, by applying all these momentum and energy conservation, energy we have not done it yet, but we will do it. What we are trying to establish is that this scattering process or this collision process indeed is like two balls colliding in classical physics, where we apply classical laws, conservation laws, or that of momentum and energy. So, conservation of energy, but now you have to think about using relativistic expressions. So, this tells you that E0 plus m naught c square equal to E1 plus k plus m naught c square again. So, this is incident photon has energy because it is coming from a source. Okay. Incident photon, this is the rest mass, sorry, this is electron, there is the rest mass energy of the electron because it was at rest. So, that is rest mass energy. This is that of the scattered photon. This is the recoil electron kinetic energy. And this is again the rest mass energy of electron. This term will not be there for photons because photons have 0 mass. So, this will tell you that E0 minus E1 that is equal to k, and let us call that as equation 4. Okay. So, the relativistic expression for energy is, so generally I mean relativistic energy is equal to E is equal to P square C square. This for a general relativistic particle, like for the electron this will be there m0 square C4. So, this is equal to E square. So, for photon of course m0 equal to 0, m0 equal to 0. So, E is equal to Pc. So, P is equal to E over C. This is equal to H nu over C. Okay. So, let us call this as equation 5. From 4 and 5, we have a C P0 minus P1 that is equal to K, that let us call that as equation 6, and for electron the energy is K plus m naught C square whole square, that's E square, is equal to P square C square plus M naught square C4. Okay. And if you open the bracket and simplify, this will simply give you a k square plus 2k m naught c square plus p square c sorry, this is equal to p square c square, because the other term cancels. Okay. So this tells you that k square over c square plus 2k m naught equal to p square. Let's call that as equation 7. Okay. So putting now p square on the RHS of 7 from 3. So from equation 3, let's see where equation 3 is. That's the p square that you see there on the right hand side. So you put that into the this right hand side of this equation 7, and what one gets is and also k from 4, k from 4. Okay. So these have to be put in the right hand side of 7, and that will tell you that one gets this equation, which is equal to p0 minus p1 whole square plus 2 m naught c p0 minus p1. This is equal to p0 square plus p1 square plus 2 p0 p1 cosine theta. Okay. Simple algebra, but you have to do it carefully in order to get all the terms correct. So if you simplify, then what happens is the following. M0C P0 minus P1 equal to P0, so this minus. So P0 P1 into 1 minus cosine theta, and so 1 over P1 minus 1 over P0, that's equal to 1 over M0C and 1 minus cosine theta. Okay. And if you multiply it by h and on both sides, and if you recognize that h over P1 so h over P1 is lambda 1, h over P0 is lambda 0, which are respectively the lambda 1 or lambda prime. Did we say okay, so let's call it as lambda prime and this as lambda. Okay, so lambda prime, which is the scattered photon wavelength, and this is lambda is the incident wavelength of the photon. I think that's what we have started with, or we might have started with. Okay, so there's lambda and lambda prime, correct. So this means that we have lambda prime minus lambda equal to delta lambda. This is equal to h over M0C and 1 minus, so there is a 1 over, this square will not be there, h over M0C 1 minus cosine theta, and this is written as lambda c 1 minus cosine theta, and so lambda c is equal to h over M0C, which is called as the Compton wavelength. So this 2.43 into 10 to the power minus 12 meter equal to 0.0243 angstrom, and this is called as a Compton wavelength. Okay, so so this is delta lambda is called as a Compton shift because of Compton, you know, they performed this experiment. This is called as a Compton shift, and interestingly, this shift, this depends on theta but not on phi. So, we are only concerned with the scattered photon and not with the recoil electron, and there are two limits that can be seen, which are one is that for theta equal to 0, we have this called as a grazing collision. That is after the collision it does not change the direction, then there is no change in the Compton wavelength, and there is for theta equal to pi, that means that it is kind of returns back in the direction of this incidence, and then delta lambda is equal to twice of lambda c, and that is the maximum value. Okay. So, what it means is that there is this if you plot delta lambda versus theta, then it sort of looks like like this. Okay. So, this is that maximum value which is at pi, and somewhere in the middle is like pi by 2, and this is 0. Okay. So, this is what the scattered or the difference between the wavelengths before and after scattering, that looks like this, and which is proportional to 1 minus cos theta. So, this is Compton effect, and we can quickly go through the photoelectric effect, which was performed by Hertz in 1886, in which there is a source of radiation which can be a bulb or which can be any source that you can think of, and there is a metal plate which is called as a cathode plate here. So, this is the metal plate, it incidents on a metal plate, and there is an anode. So, there is an electron that is ejected from the metal plate and it moves towards anode, and there is a variable voltage source that you have here, and this is like a glass chamber. Okay. And this was done by Hertz in 1886. So, what happens is that, so light falls on a metal plate, number 2, electrons are emitted, and finally collected by I mean they are sort of, this thing is connected to say a galvanometer or an ammeter, which is connected to the cathode, to the anode, sorry. Okay, so this is the situation that we have, and what else do we have? We have one finds that there are two observations mainly. So, one is that if you make this metal plate that you see here to be more and more negative with respect to the anode, which is done by this voltage that you see down there, then the photocurrent, that is the current due to the emission of the electrons and which go and deposit in the anode, and anode is connected to a measuring device of the current, that current completely stops for a given this stopping potential, this called as a stopping potential. So, if you make it negative and make it negative enough, and then the photocurrent stops, and this photocurrent is performed for say two intensity, let us call it as a I1 and I2, where I1 is greater than I2, it has the same stopping voltage. Okay. So, this is one of the things that is of importance here. And not only that, if you increase the potential difference, it sort of increases linearly at the beginning, but then it saturates at large potential difference. So, this photocurrent has no dependence on the potential difference that is applied between the metal plate and the anode. Okay. So, this is basically this is the applied potential difference, you can call it as a applied potential difference. And what is another important thing is that the maximum kinetic energy of the photoelectron, let us call it as a K max, that is equal to EV0, or which let us call this as minus V0, okay, instead of delta Vs, minus V0. So, it is equal to EV0 and is independent of the intensity of light. This is what has been told, that is whether it is a high intensity or low intensity, this is same. Okay. So, what is the question then? The question is that whether these observations are consistent with the classical theory or the classical ideas that we have so far. Okay. And in order to strengthen that, what Millikan did, this is done somewhere around 1923, but Millikan I think 1914, not 1923, but he got the Nobel Prize in 1923. So, what he did is that he wanted to know whether these the stopping potential is associated with a cutoff frequency, okay, and how it depends on the cutoff frequency. So, what he found out is that if you have this stopping potential, which is that V0, so the stopping potential and the frequency. Okay. So, this stopping potential is associated with a cutoff frequency nu 0, okay, below which there is no photocurrent that is observed. Okay. And he performed this experiment, Millikan, for sodium, where nu 0 was observed to be 5.6 10 to the power 14 hertz. And this is basically the V0 versus nu, which shows a straight line behavior with a stopping potential to be at nu 0. Okay. And this has won him the Nobel Prize, and we are asking this question, that what are the abnormalities with regard to classical theory, or what cannot be explained with regard to classical theory. So, the abnormalities that we have, that K max, that is the maximum kinetic energy of the electrons, should have been proportional to the intensity of light. It is not, as we have shown that that there is for two different intensities, they merge at the same value. Second is that there should have been no cutoff frequency. That is, there should be, classical theory would say that if you impinge it with a very small frequency also, it will eject an electron, but that does not happen. And if you apply classical wave theory, then it would demand that there is there should be a time lag between incidence and ejection. But there is no time lag that was noted, and this is where Einstein came, and Einstein proposed that this kinetic energy of the electrons is equal to h nu minus some w, where w is called as a work function. And what it means is that there is the work required to eject an electron from the metal surface. Okay. And so, the maximum kinetic energy should obey this h nu minus some w 0, and w 0 is a property of a metal. I mean, basically this w 0 is the work function, it's a property of a metal. So, it will vary on which metal you are talking about. So, it will vary, the value will vary from one metal to another. And if you substitute W 0 is equal to the stopping potential E V 0, then the kinetic energy, the maximum kinetic energy to be equal to the stopping potential. So, then E V 0 is equal to h nu minus W 0 and V 0 equal to h over E into nu minus W 0, and this is the equation that Millikan found. Okay. So, once again what we have done is that we just said that this is the experiment that you have, very simple looking experiment. There is a metal plate which is called as a cathode plate, which is full of electrons. So, there is a source of radiation which incidents on the metal plate, electrons are ejected, electrons go towards the anode, get collected, and there is a ammeter or a galvanometer that is connected, which measures the current. If you make this cathode plate or the metal plate to be more and more negative with respect to the anode, then after a certain or at a certain value of this applied voltage, the current stops, and it is independent of the intensity of the light used, and this K max is equal to E V 0, which is what comes out, and which is what we have seen as well. Okay. Millikan extended this and wanted to find out whether the stopping potential has any dependency on the frequency of the radiation or the light, and he found that there is indeed a stopping potential nu 0, below which there is no emission of or I mean for frequencies to be below nu 0, no photoelectrons will be ejecting out of the metal plate. And this led to a few abnormalities with regard to what we already know, and one of them is that K max should have been proportional to the intensity of light, which it is not. The two intensities or any intensity that you use would have the same stopping potential. There should have been no cutoff frequency, because that is what classical theory says, and there should be a time lag between the incidence of photon and ejection of photoelectrons. Okay. None of these are seen there. So, Einstein said that let us have a relationship between the kinetic energy of the ejected electron and the frequency or the energy of the photons by this relation, which is h nu minus w, and this w 0 is called as a work function, which is a property of the metal, and by putting in K max equal to E V 0, we got a nu 0 or rather the V 0 to be having this E here as well. So, V 0 to be proportional to nu, and this there is also a constant there which is found in this the work by Millikan. So, once again we have applied the conservation of energy and treated this problem as if there is this photon and electron, the collision is like the scattering between or collision between two spheres, and we have gotten this result which is seen in experiments or rather observed in experiments. And so, there is a triumph of the particle nature of radiation, but we will have to also see that in some other experiments it shows up as waves. We will see that later. That is all for today. Thank you.